Every single radioactive element will decay at a very predictable rate, and that really depends on which element we're talking about. They're not all the same. Um, there is no way that we could increase the rate of decay or even decrease the rate. You could put it on the greatest amount of pressure or the greatest amount of temperature or anything you could possibly think of. But since we're talking about nuclei being unstable, no chemical reaction or any other physical interaction can change the rate at which they decay. And that is somewhat convenient for us because, again, that could serve as kind of like a clock. Because no matter what has happened throughout our history of our planet, the atoms that make up this planet are, well, at least the radioactive ones, will decay at a very predictable rate, whether we're talking about in 2021 or we're talking about back when the dinosaurs were here or back when this planet was mostly covered in shallow oceans. The rate of radioactive decay is a universal constant across, well, the entire universe. So the way we're going to measure the rate at which something will decay is something called a half-life. A half-life is the time it takes, I'm just going to put that, the time it takes for half of the substance to decay. Okay, so we're not going to measure how long it takes for the entire substance to decay, but literally half of it. We call that a half-life. The symbol right here that you see next to that is called lambda. Again, that is the Greek letter for L, lambda, and that's the symbol for half-life. Now, as you see in the image right here, let's just say we're starting with 100%. As you can see in this image here, we have all of those dots are red. Now, after one half-life, you're going to end up with not 100, but now 50. So we have decayed from 100 to down to 50 in one half-life. After the second half-life, then we're going to be exactly half of the previous. So we're going to go from 50 all the way down to 25. So now we're down to half of 50, which is 25 after two half-lives. After three half-lives, what's going to happen is we're going to go from 25 to half of that, which is 12.5. They rounded up to 13. 12.5, and you guessed it, after four half-lives, we're going to do half of 12.5, which would be about 6.25, which they rounded down to 6. So every single time we have a half-life, it cuts what we have at that moment down by half. So the pattern would go from 100 to 50 to 75 to 25 to 12.5 to 6.25 and so on. Half of that, half of that, half of that. Now again, what is unique about that is the time it takes for this to this to this is all exactly the same. The time between one half-life and any other half-life is always the exact same amount of time, each time losing half of the radioactive isotopes that we have as they decay into the more stable form of that isotope. All right, so that is the premise behind the half-life. So let's go ahead and try a little bit of the math. Now, again, to put a little more context into this, we could use radioactive dating and half-lives in order to say, in the more common examples, is looking at how old, say, a dinosaur bone is. Whether we measure the rocks above and below the fossil or the fossil itself, we could see how much of the radioactive isotopes are gone. Therefore, we have a very good idea of how old it is. And we do that based on its relationship to what the stable isotope is. And so for what I'm trying to get at is, while we are alive on this planet, the ratio of, say, let's say carbon-12, which is the stable form of carbon, and the radioactive form called carbon-14, that ratio is always the same. And so from the time that you were born until the time that you die, we are always consuming a very consistent ratio of carbon-12 to carbon-14. That always stays the same because everything we eat, everything we consume through our entire lives has the same ratio of stable carbon-12 to unstable carbon-14. Now, the moment that we pass away and we die, well, we stop consuming. Therefore, the carbon-12, which is stable, will stay consistent throughout, let's just say we're fossilized, and then the amount of carbon-14 will decay over time. So your carbon 12 is going to be consistent because it's stable. Carbon 14 will slowly decrease over time. And so then we're able to say, okay, we know that the ratio of carbon 12 to carbon 14 at the time that organism was alive was this, because again, it's always been the same. But now in the fossil of Mr. Wyant, the ratio of carbon 12, the stable form, to carbon 14 is now that. So then we can compare, okay, if it was this when Mr. Wyant was alive and it's this now that he is a fossil, then we could see, okay, how much time has passed, how many half-lives have occurred, therefore, how old is the fossil of Mr. Wyant? So that's basically the premise of it works. The clock basically starts when the organism dies, because while they're alive, the ratio of carbon 12 to carbon 14 is consistent throughout their life. I hope that makes some sense. But now this is not only true for, say, biological tissues, we could also use this for rocks. We could use this for a whole bunch of things. But we'd have to use a different isotope based on the number of, or the length of their half-life. Carbon 12 and carbon 14, their half-life is 5,730 years. And that is not going to be long enough to date rocks, which are millions and millions and millions of years old. In fact, way, way, way older. So let's go ahead and jump into this. So we have this really nasty looking equation at the top of your screen. It's not as hard as it looks, but it definitely looks hard. What we have here again is NT stands for the quantity of the substance that is remaining. So this whole equation is saying how much do we have left over after the number of half-lives, okay? N naught or N sub 0 is the initial quantity of the substance. So this is our starting substance. NT is our final remaining amount of substance after X number of half-lives. T, which is over here in this exponent, the top of the exponent is going to be the time that has passed, and the denominator of the exponent will be the length of the half-time of that particular substance. So that looks really hard, but again, algebraically, it's not too difficult. It is going to be a little tricky though when we put it in our calculator, and I'll explain that in a moment. So for number one, we have potassium 40. Remember, 40 is the mass of potassium because we already know the atomic number of potassium. It has a half-life of 1.25 billion years. That's pretty long, which makes it very useful for dating ancient rocks. Again, carbon 14 with 5,730 years isn't going to be long enough. What percentage of carbon 40 is remaining in a meteorite that is 2.45 billion years old? Okay. All right. So what I would like to do is basically compare the two numbers, the two ages. We have 1.25 billion and 2.45. I know that if I double 1.25, I would get 2.5. And 2.5 would be really nice because then I would know that if it's 2.5 billion years old, that would be 2 half-lives. That would be pretty nice because again, if I multiply this by 2, that equals 2.5. And that would be nice if this was 2.5, because then that would be, again, 2 half-lives. Well, it doesn't work out quite that nicely. So we're not going to be able to use logic for this problem. We're actually going to have to do a little bit of math. Let's go ahead and try to put all this information into our equation. So NT is the quantity of the substance remaining. Well, the question's asking what percentage of potassium 40 is remaining. So we don't know NT. So I'm gonna go ahead and put NT like this, or again, that's basically our X, of course. Next, we have our initial quantity of the substance. So it doesn't really tell me that, does it? Because it says potassium 40 has a half-life of that, which makes it useful, blah, 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 blah. What percentage of potassium 40 is remaining? And then they give us the duration of the time elapsed. Well, they don't give us the amount that we initially started, but they kind of do because they're asking for a percentage. If they're asking for a percentage, then wouldn't the original be 100%? If the original is 100%, then whatever is left over, called NT, would be the remaining percentage, which is what they want. So we could kind of basically use 100 as our starting amount because that's how percentages work. So N naught is going to be 100. I'm going to multiply that by 1/2, and then I'm going to raise that to T, which is the time elapsed, which is 2.45. 2.45 billion years divided by my half-life, which is 1.25 billion. Now, I don't need to put billion and 6 zeros after that because it's all going to cancel out, right? So 2.45 billion over 1.25 billion is the same thing as 2.45 over 1.25. The zeros will cancel out, so I'm just going to leave that billion out. Now, if it was billion and million or billion and thousand, that's different. But billion, billion, it's the same thing. Okay, so to get this into be NT, in my calculator, this is what I'm going to type into my calculator. I'm going to do 100 times parentheses 1 divided by 2 parentheses caret top parentheses 2.45 divided by 1.25 close parentheses. So that's how I'm going to type it into my calculator in order to get it right. The 1/2, 100 times 1/2, that needs to be in parentheses because again, that's showing a half. Then you're going to do the caret top, meaning raised to the power of, open parentheses again, do the division of the exponent, close parentheses, and that will work. So 100 times open parentheses 1 divided by 2 close parentheses caret top exponent open parentheses 2.45 divided by 1.25 close parentheses. Whew, all right, what I get is 25.7%. Now again, let's go ahead and ask ourselves, does that answer make sense? So again, we said 1.25 times 2 is 1.5 or 2.5, which is almost the amount of time that's passed, meaning we had almost gone through 2 half-lives. 2 half-lives, again, if I'm going to use my graph here, this is my half-lives, or let me go ahead and just use lambda instead of HL. My half-lives, and this is my quantity or abundance. So if I start at 100% and I go to 1 half-life, that would go to 50, so right about there. Then if I do another half-life, it'll go from 50 down to 25, right, which would be right there. Okay, so meaning if I do 2 half-lives, we should be about 25. Notice my answer is 25.7. So that makes a lot of sense. Our percentage that is remaining is about a quarter of what we started, which is just a little bit under 2 half-lives. So my answer using logic makes sense. My answer using math really makes sense. So I feel very confident on that problem. Again, the only really difficult part of that is how to put all that jumbled mess into the calculator correctly without making any mistakes. All right, let's go ahead and try the next one, number 2. So here we have, I'm going to go ahead and write the equation that way we have it. I'm going to go ahead and put that up here. So we have NT equals N naught multiplied by 1/2 raised to the T divided by T half-life. Okay, that's the equation. Again, this right here is, of course, an exponent. I should have wrote that a little. Let me go ahead and fix that just so there's no confusion. So let me write that up here in the corner. So T over T 1/2. That's an exponent. Okay, jump into number 2. It says a 10,000-year-old fossil leaf is found to contain 87 grams of carbon-14. Given that the half-life of carbon-14 is 5,730 years, how much carbon-14 did the leaf contain when it was alive? So we're looking for the original, and we have the final. So NT is the amount that remains after. N naught is the amount that we that we started with, which is exactly what it's asking for, multiplied by 1/2, raised to the power of the amount of time that has passed, which is 10,000 years, divided by its half-life, which is 5,730 years. All right, so to do this, again, don't forget this is an exponent, 10,000 over 5,730 years is an exponent. So to do this algebraically, what I think I want to do to make this easy for me is solve this part first. Then once I have that answer, I'm going to slide it underneath here to get my N naught. So I'm going to do open parentheses 1 divided by 2 close parentheses caret top open parentheses 10,000 divided by 5730, close parentheses, gives me this. So what I have is 87 grams equals in naught times 0.298. Okay, again, I'm going to move that underneath here, 0.298. That will cancel this out, giving me in naught equals 87 divide second answer 291.66 grams. All right, let's pause there and think, does this answer make any sense to me, or am I wildly off? So if we finished with 87 grams, we know our answer is going to be bigger because it's going to decay over the 10,000 years. So our answer should be bigger. So I'm not alarmed that my answer is larger than 87, as that's exactly what I would expect. Now, if the time that has passed is 10,000 and my half-life is 5,730, that means we did not fully do 2 half-lives. 2 half-lives would be closer to what, like 11,460, if I did the math right in my head, which I probably didn't. So we're not quite at 2 half-lives, we're just shy of that. So if I wanted to go backwards, I could take 87 in my calculator, 87 times 2, that's 1 half-life, going backwards up to the original. I'm going to multiply that again by 2, and what I get is 348. So if I did 2 full half-lives up, I should have started with 348, but I started with 291.66 according to my calculations, which again is less than 2 half-lives. So that does match the scenario in the question, because remember, 10,000 years is not 2 half-lives of 5,730 years. Again, that would be 11,460 again, if I'm doing the math in my head correctly. All right, now that we've done 2 like that, let's go ahead and look at our final example, which is number 3. For number 3, what we have here, nitrogen-13 is a useful radio tracer in medical imaging because it has a half-life of about just only 10 minutes. Again, therefore, we're a little bit more comfortable injecting that into a person's body because it's not going to last 5,730 years and constantly irradiate you. Therefore, it does not linger in the body for long, like I just said. How many minutes does it take for a 5 grams of nitrogen-13 to decay to 25% of its original mass? Okay, so if we try to use the original equation, our amount that remains is, well, we don't know. 25% of its original mass. Okay, we could potentially say we're going to be left with 25%. N naught is our original mass, which is 5 grams, maybe 100% times 100 or times a half, raised to the power of the amount of time that has passed. How many minutes does it take for this? We don't know. And then over here is the half-life of 10 minutes. So this is a problem because we have a percentage, we have grams, which could be replaced by 100%. We have our unknown duration, again, which is minutes. So I'm going to probably just go ahead and tackle this one a lot more simplistically using logic. Okay, so what I mean by that is these numbers are going to work out quite nicely. If we know that we have 25% of our original mass, and our original mass is 5 grams, then remember, if we do half-lives, lambda, and let's say we have 5 grams as our original, after 1 half-life, we would have half of that, like so, which would be 2.5, half of 5. If we have 25%, that means this is 50% right here. This represents 50%, right? So we need to go to another half-life, which is half of 1.25, which is 1.25. So that would be, again, another half-life. So that would be right about there. And that would represent 25%, again, half of 50. So if I'm going to do 2 half-lives, that would get me to 25%, which is 1.25 grams. And there basically is our answer. So how many, so we know it'd be 25%. That is, again, 1.25 grams. All right, so now that we figured that out, it says how many minutes does it take? And we know that each half-life is 10 minutes. So this is 10 minutes, this is 10 minutes. Therefore, to go to 2 half-lives would be 10 plus 10 or 20 minutes. There's our final answer. So that one is a pretty big departure from number 1 and 2 because we didn't have to do that ugly looking math problem. We just kind of used logic. We knew that if we're going down to 25%, that would be 2 half-lives because from 100%, 1 half-life would be 50. Another half-life would be 25%. If we were to do another half-life, that'd be 12.25% and so on. So once we knew that we were going to go down to 25%, that told us indirectly that that's 2 half-lives. So we knew that to go from 2 half-lives, and if each half-life is 10 minutes, then basically, of course, we had 10 minutes times 2 half-lives equals 20 minutes. So like I said, that's a nice departure. We would have liked to do that with number 1 and 2, but again, for number 2, 10,000 is not a nice round number when it comes to 5,730 years, so we had to do the math. I hope this makes sense again, but this again is how we use half-lives of known isotopes to measure how old something is or how long something will linger. As always, guys, thank you very much for watching.